Today I would like to demonstrate a very useful technique for generating low voltage, safe AC electric power at a scale that is suitable for lab experimentation and even for students working from home. Three-phase AC power is how most electricity in the world is distributed. It's a very efficient, very effective, very well-known method for generating, transmitting, and using electrical power. So, the challenge of teaching this in most classroom environments is that most classrooms are not equipped with three-phase power sources. The AC power that you receive from a wall socket is typically single-phase, and so if you want to demonstrate three-phase electric power, that can be a challenge. So I want to show one way to easily do that. What you see here is a pair of radio-controlled vehicle hobby motors. So these would be motors that you might use to propel a model airplane, model car, model boat, something like that. These are two different styles of motors. This is very important. Over here is the classic or traditional DC brush style motor. It has a permanent magnetic field. It has a wound armature with commutators and brushes. You power it up with DC, plus on red, minus on black, and it spins. Very simple, very proven technology, but that is being supplanted largely by more modern motor technologies used for radio-controlled cars, and that includes brushless motors. This is a brushless motor. Specifically, it is a sensorless brushless motor, and the way they work is different than the DC brush style motor. Here in the sensorless brushless motor, the rotor itself is a permanent magnet, and the stationary windings on the periphery are wound in a three-phase fashion. I'm not sure if it's a Y or a delta. I have not been able to see the data sheet for this motor. It's irrelevant, but you have three-phase stator windings inside this motor. So when used in a radio-controlled vehicle, you would have a special electronic circuit that generates the three-phase AC power necessary to power up this motor and drive the vehicle. Here, though, we're going to be using the sensorless brushless motor as a generator. So I was able to determine that there are different can styles or motor frame styles of motors, some of them that share similar dimensions. This particular brushless sensorless motor is a 3650 can style, and this particular DC brush motor is a 550 can style. They happen to share the same outside diameter, which makes it very easy to align their shafts. And I just happened to find out that both these motors sit very nicely inside a 35mm DIN rail. So I took these two motors, lashed them to the DIN rail using zip ties, and then coupled them together. I have a couple of flange couplings here, and as you can see, I simply looped a piece of 22 gauge red insulation wire through the four holes of the flanges to very crudely couple them together for this demonstration. So what we have over here is a schematic showing what's been built. Here's the DC motor, brush type, connected to a DC power supply. There's the brushless sensorless motor, which is essentially an AC motor, which we're using as an AC generator. And as we spin the shaft, because it's a permanent magnet motor, it's going to automatically generate three-phase AC. To measure this using an oscilloscope, I need to have a ground connection. I essentially need 4 wires. So I've run the 3 wires of that brushless sensorless motor to a 1 kilo ohm three-phase load. Essentially, this is a network providing a center tap ground connection for my oscilloscope. I have an oscilloscope with 3 channels I'm using. The ground connection of the scope is connected to the center of the resistive Y, and the 3 probes go to those peripheral connections. Those connections have been made over here on a set of terminal blocks, again on a DIN rail. I also have a multimeter plugged in here to measure line voltage, and let's see how this works. Here's my oscilloscope, currently showing flat line because the machine is not spinning, but as soon as I turn this on, my DC power supply, you can hear and see the motor is now spinning, and of course as the motor spins, it spins this one, which is acting as a generator. And looking at the oscilloscope, wow, we have three-phase power. You can see the 3 phases right there, clearly 120 degrees separated from one another. You can also see I happen to be measuring frequency on this oscilloscope. Currently says 58, 57 hertz. If I turn up my DC voltage of my power supply, that will cause the DC motor to spin faster. That causes the rotor to spin more frequently past the stator windings and produce higher frequency. So I can change my frequency here by dialing up my DC voltage. And if I go over here to the oscilloscope, I can dial it up until I get closer to 60 hertz. There we go, 62, I'll back it down, 61, 59.5, that's probably as close as I can get. 62, 64, whoops, overshot. But the point is, I can generate 60 hertz three-phase AC at very safe voltage levels. Now when I say safe, I truly mean safe. We are currently at 500 millivolts per division. I'm not even at one full division peak voltage, so we're looking at a very low amplitude of signal. Going over to my meter, I happen to have this set up on the 2.5 volt AC scale, and looking at that scale, we are actually less than 1/4 of a volt. Now that's not terribly useful. Not a lot of things you can power on 1/4 of a volt AC. However, this is AC, so we can step it up through a transformer network. And that leads to another experiment students could do, is to build and wire a three-phase transformer network to step up the AC voltage from this three-phase generator up into a more useful level. But really the point of this is to show how easy it can be to generate three-phase AC in a manner that is safe and effective for students to apply, whether it's in a classroom, lab environment, or even at home. Literally, you could build this using nothing but simple hand tools, and it's very inexpensive. These motors run less than $50 a piece, in some cases significantly less than $50 a piece. They're off-the-shelf parts. If you get two motors with the same can size that fit inside the DIN rail, they will automatically align to each other. And again, DC brush style motor, and then a brushless, sensorless motor, which is essentially a permanent magnet AC motor generator. So very simple.